Have you ever watched a headache tablet dissolve in a glass of water?
Oh,
You
yes.
drop it in, and it does this little fizzing dance at the bottom of the
It's
glass.
a very common sight.
And if you've ever, tasted the water, which I don't recommend, by the way, it's quite awful, you'd notice it's sour. It's acidic.
It is. And that fizz, that sour taste,
Mm.
that is literally chemistry happening right in front of you.
And that is exactly where we are going today. That simple pain relief isn't magic. It is the chemistry of the functional group we are deep diving into. Hello, everyone, and welcome back to the Deep Dive.
Hello.
Today, we are getting into Unit 8, aldehydes, ketones, and carboxylic acids.
It's a big unit. A lot of students find the mechanisms a bit tricky here.
They do. But we're going to focus on the final part of the chapter, Topic 10, uses of carboxylic acids.
Ah, the uses section.
Exactly. And I have to be honest, when I was in class 12, I always thought of this as, well, the boring part, the part you cram just before the exam.
That's the classic trap, isn't it? You spend all this time on the hard stuff, the reactions, and then you just dismiss the uses as a list to memorize.
So why is that a mistake? Isn't it just vinegar for food, aspirin for headaches?
I mean, on the surface, yes, but the uses section is the whole point. It's the so what of the entire chapter. If you understand why we use them, you actually get the personality of the molecule. Think of them less as a list and more as chemical building blocks.
Building blocks, like Lego.
Sort of, yes. Very powerful Lego. Understanding these uses connects all those abstract concepts, like acidity and esterification, to real things, to the shirt you're wearing, the food in your fridge, even the proteins in your body.
Okay, that's a big claim. So let's break this down. At the simplest level, for a student who's really struggling, what is the core idea here?
At the absolute simplest, 0 level, carboxylic acids are the world's most versatile attachment points.
A versatile attachment point. Okay, what do you mean by that?
Imagine you're building something. You need a connector piece that can do 2 very different jobs. The carboxyl group, the COO group, is that piece. It's a double threat.
A double threat, like an all-rounder in cricket who can bat and bowl.
That's a perfect analogy, exactly like an all-rounder. Look at the structure. You have the C double bond O and a single bond to an OH group. This gives it 2 superpowers.
Okay.
Power number 1 is acidity. It can give away that hydrogen ion, the H+.
Right, the acid part of its name.
That's its first move. It changes pH. It can kill bacteria. But then you have power number 2. You can actually remove that entire OH group and swap it for something else.
And that's the building part, the attachment point.
Precisely, because it can do both. Act as an acid OR, act as a gateway to build bigger things. It's used for, well, almost everything.
So if I'm trying to picture this, the carboxylic acid is like a tool handle. And I can either use its acid feature or its replacement feature.
You've got it. And if you look at your syllabus, every single use in the NCERT textbook comes from just 3 behaviors. If you get these 3, you don't need to memorize anything.
Okay, let's list them out clearly. What are the 3?
First is acidity. This is for things like food preservation.
Okay.
Second is esterification. This is when we swap the OH group. This is for making polymers, medicines.
Right.
And third is amino formation. And this is the secret to proteins, to life, really.
Acidity, esterification, amide formation. Simple enough?
The behavior drives the use.
Now, before we move on, I want to tackle a big misunderstanding. When I say carboxylic acid, I think 90% of students just think of
Vinegar.
acetic acid. And because of that, it feels like, kitchen chemistry, something low-tech.
That is a huge misconception. Yes, acetic acid is vinegar. But if you start there, you're missing the entire Industrial Revolution.
The Industrial Revolution.
I'm serious. These acids are fundamental to life itself. Your body is made of amino acids. That's a carboxylic acid. But beyond biology, they drive massive industries. Plastics, nylon, polymers. None of that exists without the COOH group.
So it's not just the vinegar in the pantry, it's the plastic bottle it comes in.
And the label on the bottle. And maybe even the shirt you're wearing while you hold it.
Okay, point taken. To help us visualize this versatility, you mentioned an analogy about electricity. How is an acid like electricity?
Well, think about the electricity in your home. It's just one thing, right? A flow of electrons.
Right.
But if you plug in a heater, you get heat. If you plug in a bulb, you get light. If you plug in a computer, you get logic. The source is the same, but the application is different.
I see. Same source, different outcome.
Carboxylic acids are the electricity of organic chemistry, one functional group.
Yeah.
But if you use its acidity, you get food preservation. That's like using electricity for heat. But if you use its esterification property, you get polymers, like nylon. That's like using electricity for light. The application depends on which property you tap into.
That clicks. You also mentioned another analogy, the multi-tool.
Yes, the Swiss Army knife. This is great for exam recall. Just imagine the COH group is the red handle of the knife.
Okay, I'm picturing it.
Now, you need to stop your bread from getting moldy. You pull out the blade-marked acidity, problem solved.
Simple.
But now you need to make a polyester shirt. The acidity blade is useless. So you fold it in and pull out the big saw-marked esterification. You start linking molecules together.
And what if I need to make soap?
You pull out the little screwdriver attachment marked salt formation.
I love that. So you're not memorizing a random list, you're just remembering which tool to use for which job.
Correct. And this versatility is why this concept even exists, historically.
History.
Just for a moment, think about it. We've been using acetic acid vinegar for over 5,000 years. Ancient Babylonians used it for pickling. They didn't know the chemistry, but they knew it worked.
Right, classic use.
But then, fast forward to the 1930s, the industrial boom, and suddenly chemists figure out they can take a dicarboxylic acid, adipic acid, and react it to make nylon?
Nylon, like the fabric.
Ropes. All of it. It was a revolution. It shows the shift from a simple kitchen use, like vinegar, to deliberate advanced industrial technology. We went from pickling mangoes to building parachutes with the same family of chemicals.
Wow. From mango pickles to parachutes. That's quite a journey.
It is.
Okay, let's make this even more real. I want to run a little mental movie.
Let's do
I
it.
want everyone listening to just picture a normal day. Let's call it Spot the Carboxylic Acid.
Yeah.
You're a class 12 student. Alarm goes off.
Okay.
Scene 1, morning. You stumble to the bathroom. You wash your face with one of those anti-acne face washes, and it stings a little. What's that?
That sting is probably salicylic acid. It's a carboxylic acid that's helping to peel away dead skin cells.
Okay, face washed with acid. Now, my head hurts from studying. I take an aspirin.
That's acetylsalicylic acid. You've just swallowed a carboxylic acid derivative to stop your pain.
I go to the kitchen, pour a glass of juice.
Citric acid. Gives it the tart taste.
Okay, scene 2. Getting dressed for school. You put on a shirt. It's maybe a synthetic blend. Doesn't wrinkle easily.
That's likely polyester.
And polyester is from...
Paraphthalic acid, or maybe your socks are nylon from adipic acid. You are literally wrapping yourself in chains of carboxylic acids.
That sounds slightly alarming, but I get your point.
It's very stable, don't worry.
Okay, final scene. Evening. You grab a slice of bread. It's been sitting out for a few days, but there's no mold on it.
You can thank propionic acid for that. It's added to bread to stop mold growth.
And finally, wash my hands with soap before bed.
And that soap is just the sodium salt of a fatty acid. And a fatty acid is just a carboxylic acid with a very, very long tail.
So from waking up to sleeping, washing, eating, dressing, it's everywhere.
Exactly. It proves this topic isn't just for an exam. It's woven into the fabric of your life.
That really brings it home. Let's dig deeper into 2 of those. Aspirin. It's a classic example. Why does it actually work?
Okay, so this is a great observable phenomenon. You see the tablet fizzing in water, right?
Yeah.
That's the acid reacting. But inside your body, the aspirin molecule, acetylsalicylic acid, it fits perfectly into an enzyme.
An enzyme.
Let's just call it the pain enzyme. This enzyme is what creates the signals for pain and inflammation. Aspirin just jams it. It blocks it from working.
And the acidity helps with that.
The acidity is part of the package. It helps with how it gets absorbed and how it interacts. The same property that makes it fizz in water helps it shut down your headache.
Amazing. Okay, let's talk technology. Polyester. Everyone wears it, but what is it?
This is where we get into polymer chemistry. The polymer is PT polyethylene terephthalate.
PT. That sounds complicated. Break it down.
It's actually quite simple. You take a molecule of terephthalic acid. It's a benzene ring with 2 COOH groups, like arms sticking out on opposite sides.
Okay, 2 arms. A dicarboxylic acid.
Right. And you mix it with an alcohol, ethylene glycol.
And they just link up.
They react. It's that esterification reaction again. An acid arm grabs an alcohol arm, they link, and a water molecule gets kicked out.
And because it has 2 arms?
Exactly. It can grab another alcohol on its other side, and that alcohol can grab another acid. And you get a chain reaction. Millions of them linking together, and you get this long thread-like molecule. You spin that into a thread, weave the thread, and you get polyester fabric.
So my wrinkle-free shirt is just a massive chain of reacted acids and alcohols.
That's all it is.
There's something counterintuitive here, though. You look at these formulas, CHO, Simple stuff.
You might think that. You might think, oh, it's just organic chemistry, it's just vinegar. But actually, terephthalic acid and adipic acid, they are produced in billions of tons every year.
Billions.
Billions. With a B. It's counterintuitive that such simple molecules are the backbone of the massive global textile and automotive industries.
That is fascinating. It's the power of linking them together.
Exactly. Strength in numbers.
Okay. We've understood the concepts. We've seen the mental movie.
Yeah.
But our listeners have the board exams coming. They need the mark scoring section.
The money lines, as you call them.
Yes. What are the key sentences they must write to get full marks on this question?
All right, let's slow down for this. These are your clarity lines. You must be specific.
Okay, let's go. Use number 1. Food.
Don't just say used in food. Write this. Carboxylic acids like acetic acid, citric acid, and propionic acid are used as preservatives because their acidity inhibits microbial growth.
The key word is acidity. And mentioning propionic acid sounds smart.
It does. It shows you know more than just vinegar.
Okay. Use number 2. Medicine.
Many drugs, like aspirin, acetylsalicylic acid, are carboxylic acids or their derivatives.
Simple and to the point. Use number 3, the big one, polymers.
Dicarboxylic acids are used in polymer synthesis. Adipic acid is used to make nylon 6,6. Terephthalic acid is used to make polyester, PET.
And the key here is not to mix them up. Adipic for nylon, terephthalic for polyester.
My trick for that is terephthalic sounds a bit like terrible. And some of those old polyester suits were, well...
Terrible. Okay, I'll remember that one. Terrible polyester. Got it. Use number 4. Soaps.
Fatty acids, which are long-chain carboxylic acids, are converted to sodium or potassium salts to form soaps.
Perfect. And finally, number 5, biology.
All amino acids contain a COOH group, making them fundamental to protein synthesis.
Fantastic. Those 5 lines are the key to full marks.
Absolutely. No fluff, just the facts.
We're almost at the end.
Yeah.
Let's do a super quick recap. A student has 10 minutes before the exam. What do they need to remember?
I use the mnemonic pharma-food polymers life.
Pharma-food polymers life. Okay, one last time.
Pharma, aspirin, food, vinegar, preservatives because of acidity, polymers, nylon from adipic acid, polyester from terephthalic acid, life, amino acids and fatty acids for soaps.
Pharma-food polymers life. And remember the multi-tool analogy. One group, COOH, many different uses.
One structure, infinite uses.
Before we sign off, I want to leave everyone with one final thought. We've talked about aspirin, about nylon, but consider this.
Right now, as you're listening, your brain is working, your heart is beating, you're using energy. How?
I have a feeling you're going to say it involves carboxylic acids.
It does. It's a process called the citric acid cycle.
The citric acid cycle. We mentioned citric acid in juice. It's inside us, too.
It is the central engine of your metabolism. The very energy allowing your brain to process my voice right now comes from your body breaking down and rebuilding carboxylic acids inside your cells. So, this topic, it's not just something you study for life. In a very real way, it is your life.
That's a powerful thought to end on. You are literally powered by this chapter.
Chemistry is everywhere.
Thank you so much for joining us on this deep dive. We hope you're feeling ready to crush those exam questions on the uses of carboxylic acids.
Study hard, keep those structures clear, and all the best.
See you in this deep dive.